Similar polygons. Well, any polygons which are similar are polygons or shapes which share the same shape but aren't necessarily the same size. A very practical example of that would be models, scale models. Whenever we're dealing with similar shapes of things, we need what's called a scale factor, or a constant of proportionality. It's basically the relationship between the two figures. For the models here, this is a Lamborghini, each of these models has a different scale factor. The first one is 1 to 18, which means it's 1/18th the size of the original car. The next one is 1/24th, which means that it is 1/24th the size of the original car, or every part of it, all its corresponding parts, is 1/24th the size of the original object. So when we're talking about polygons, for example, the angles of a quadrilateral are in a ratio of 1 to 2 to 4 to 5. Find the measure of the largest angle of this polygon. We need to figure out what that missing scale factor is between this proportion and the actual angles in order to figure out what the actual measure is. Well, in order to do that, there's a key piece of information here, which is that these represent each angle of the quadrilateral, and the sum of all angles in a quadrilateral is 360 degrees. That is a 3. I'm sorry, my handwriting is god-awful. But 360 degrees is the sum of all the angles in the quadrilateral. So what we're going to do is introduce this scale factor into this proportion. So 1 to 2 to 4 to 5 is actually the same as x to 2x to 4x to 5x. And we know that the sum of all of these things will add up to 360. Again, this x is representing that missing scale factor, that constant of proportionality that we don't know. So the sum of these has to be 360 degrees. When we add up the left-hand side, we get 12x, which when we divide by 12, we find that x is 30. And since the largest angle will be the 5x, the actual angle we're looking for, and the measure of this largest angle, is 150 degrees. This constant proportionality or scale factor times that largest ratio portion of the angle. Remember that for similar polygons, the ratio of corresponding side lengths is equal within each other. What that means is that each side is proportional to its corresponding side, so the ratio of any two sides of one polygon will be equivalent to its corresponding sides of another. It's also true for its perimeter. So for this example here, the sides of a triangle are 10, 12, and 14. That makes the, and find the length of the shorter side of a similar triangle whose perimeter is 72. Well, the perimeter of the triangle we're talking about first is 36. 12 plus 10 plus 14 is 36. So these perimeters should be proportional to the ratios of the corresponding sides in each of these triangles. So the ratio I could set up is 72 over 36 would be proportional to x, this shortest side that I'm looking for, over 10, which is the shortest side of the other triangle. Then it's just some simple math to figure this out, that my... Okay, there we go. That x is 20. The way we get that is we multiply both sides of this ratio by 10 and then reduce. So 10 to both sides, so that these 10s will cancel out, leaving me with x. Over here, common factors, 72 over 36 is a common factor of 36, and 2 times 10 is 20. This is how we're getting x is 20. We can also use this not just for perimeters, but for individual sides. For example, in the second question, ABCD is similar to PQRS. Now recall that when we label similar polygons, corresponding similar parts correspond to the other similar parts, so that AB will correspond to PQ. Similarly, if we get this out of the way, BC will correspond to QR. That's where we get this ratio. AB over BC is proportional to PQ over QR. When I fill in my missing parts to that, I get the following ratio. AB over BC is proportional to PQ over QR. If I want to solve this, I can cross multiply or use that property of proportions. The product of the means equals the product of the extremes. So I'll end up with x times x plus 4 is equal to 2 times 6, or 12. So I get a quadratic equation, x squared plus 4x. If I bring this 12 to the other side, minus 12 equals 0. When I solve quadratic equations, I have those 4 methods for solving. This one is actually factorable. X plus 6, x minus 2 will give me a sum of positive 4 and a product of negative 12. So that means that either x equals negative 6 or x equals 2. Unfortunately, since x here is representing the length of a side, lengths cannot be negative, so I'm going to reject this negative answer, and I'm left with x equals 2. The triangle proportionality theorem and the triangle angle bisector theorem. Now these are two other situations that give me sets of ratios that don't necessarily give me similar polygons or similar triangles, but I can also set up proportions using these two theorems. The triangle proportionality theorem is a biconditional statement. XY is parallel to AC if and only if EX over XA is proportional to BY over YC. So what it's basically doing is cutting this triangle, its sides into proportional lengths. DX, BY, XA, YX. A similar theorem, but not really related, is that the triangle angle bisector theorem. If angle 1 is congruent to angle 2, then I'm going to get proportional lengths. So these two angles being congruent, imply that AB over AP will equal BC over PC. Now, one thing to keep in mind with this theorem is that these triangles are not similar. ABP is not similar to CBP, but this angle bisector is cutting these lengths of the triangle into a proportion. So we can use these to tackle these two questions, which I'm going to allow you to try on your own. We will go over questions 1 and 2 in class tomorrow. So pause now and try those two. Okay. Then we're going to move down here to these last two things that I want to go over. Ways of proving two triangles are similar. We have the angle-angle similarity postulate, the side-angle-side similarity postulate, and the side-side-side. What you need for each of those things, for the angle-angle similarity postulate, the first one, simply two angles, any two angles in one triangle similar to the corresponding angles of another triangle. That will allow you to conclude that the triangles are similar, not congruent, but similar. For the other example, the side angle side is if you have a ratio of sides. So that would be, say again, I have two triangles. I'm going to copy this triangle so I can use it. I'm going to make them different sizes so to emphasize that they're similar but not congruent. But let's call it A, B, C, and A prime, B prime, C prime. I'm using the primes notation to see which sides correspond more easily. In the side angle side, if I know that AB over BC was proportional to A prime, B B prime over B prime C prime, and the included angle between those sides that I have, so it would be this angle, angle B, and angle B prime. If I knew that those two angles were congruent, angle B is congruent to angle B prime. Given this piece of information and this piece of information, I can conclude that these two triangles are similar to each other. The last piece of information, or the last way to prove triangles similar, is the side-side-side postulate. That's if I have no angles, but I know that all three sets of sides are in proportion, I can conclude that the triangle is similar. So all three of these allow you to conclude that one triangle ABC is similar to another triangle, A prime, B prime, C prime. Finally, what does it even mean to be similar? The definition. Well, if two polygons are similar if and only if, again, it's the definition, so it's a biconditional statement, corresponding angles are congruent and corresponding sides are in proportion. Like these two figures, if I were to overlap these over each other, notice that this angle is congruent to this angle is congruent, this angle is congruent, but these sides are only in proportion.